Welcome to this session. I'm excited to get started, but we'll go through some preliminaries first to set expectations and get some terms straight that we'll need throughout the talk. Now, this is a runtime performance talk. Whenever I say performance, I mean runtime performance and not compile time or the accuracy of some algorithm. We'll see methods to improve runtime performance by reducing the number of allocations made by containers. And along the way, I'll try to give you some hints how to use certain tools in order to observe these improvements. To put it into a broader context, we really focus on a small subset of possible perf tweaks. And I'd like to point out in particular that whatever I show you, the behavior of the allocation is never changed, right? It's always the same way of requesting memory from the system. What we do instead is methods that are completely unaware of allocators, or we use polymorphic memory resources from the standard library, mostly as is, with only very little tweaks. Now, why do I care? First of all, it's fun to think about performance. I guess it's easy to agree on that. I also happen to work on autonomy software, specifically in Oxbotica's perception team. Our software would usually listen to some input sensors, make some sense out of the data, and pass that intelligence on to some other parts of the software stack that would then, associate objects over time, do predictions, and so on and so forth. We want our software to run as fast as possible in the perception team for the obvious reason that we can't be behind the sensor input frequency. But more importantly, for safety reasons, we need to enable immediate decision making, right? How do you do that? Fast code. One more reason to care about performance might not be so obvious. Runtime performance is quite an accurate proxy measure for power consumption. And we would like this software to be usable on a range of systems, not just like a huge vehicle with a massive power supply and a big compute in the back. And we don't want to be in the situation where we say, unfortunately, our software can't run on this smaller robot because we use std list everywhere and it's like it doesn't work, right? Okay, let me plug this since we are here. Our company is hiring. Go check out the open vacancies. It's a great company. We have a high quality code base, world-class build configuration and dependency management. I think that really makes for happy developers. If you happen to be in Switzerland or would like to work there, check out Plexim. That's my previous employer. They didn't ask me to plug this, but I know they're always looking for good developers who aren't scared of C++ or differential equations. And yeah, likewise, good code base and a brilliant team. So do check them out. You can reach out directly or through me. This is my user handle on these platforms. Don't go there to look for fancy stuff in the repos. Like that's full of outdated sins from the past. But if you know how to use Git, you can grab my email address and contact me. Okay, enough of that. Let's get started. What do we mean by allocation? This term might be a bit complicated in C++ because we have this concept of an allocator. And the allocator has a member function called allocate. And that member function gives you memory that might have been allocated on the heap. It might be stack memory too. You could even, it could even hand out memory that's dynamically allocated on the stack if you do that kind of thing. But we ignore all of that and say to allocate for us means to get memory from the free store, the heap. Right? We can use several interfaces to do this. The C standard library, which you see at the top of the slide, we can use operator new, its array counterpart, or an allocator. How does the implementation usually works? First of all, operator new can be implemented in terms of the C standard library. That's malloc and friends. It doesn't have to, but it usually is. And malloc itself will periodically request memory from the underlying system. On Unix, that's through the system calls BRCAR and mmap. And then it manages these larger memory chunks and gives out smaller chunks to user applications that ask for it, right? So it needs to do the bookkeeping, metadata, tagging, and whatnot, but it also needs to do more. And we can see from the function signature that we have no state associated. It's a free function, right? So the only state that malloc can use is either global state or thread local state. And we certainly want malloc to be usable in a multi-threaded context. That means malloc has to do a certain synchronization efforts to make it safe. And this is why we can consider a call to malloc being potentially costly, right? Last note, there are more options than this to allocate memory. They're usually platform specific, like on macOS you would have malloc, zone, create, blah, blah, blah. But we don't need to look into this here. Now, since I explained the heap, I will quickly go over what I mean by stack. Stack memory is memory in the very same process memory than the heap. It just lives somewhere else within that space and is managed differently. This management is usually much simpler. Stack memory is scoped to a function, and when the function returns, the stack memory is automatically freed. And this is why we usually can consider stack memory to be cheap and fast, but also limited in size. In this example function, to illustrate that, I have depicted two objects that live entirely on the stack. And in the bottom of the other half of the function, we have objects where there's a small part on the stack that refers to memory allocated on the heap. And on the right-hand side, you can see a possible stack layout on a 64-bit machine. There might be padding in between, but this is how it could look like, okay? Just to get an idea. And you can probably tell from what I've said so far that I don't work with microcontrollers and all. I hope that my methods will somehow translate to smaller devices. If they don't, let me know. I would be interested to hear about it. Okay, this slide mostly doesn't make any sense, but since I introduced heap and stack, I thought I should also mention containers. The only thing to take away from here is that we will use some non-standard container. Mostly in the examples is always boost. I hope using boost doesn't make you angry or anything. I don't see like people shaking fists, so it should be okay. All right. Recipe 0. We start with a question. How many times will this allocate? Yeah, 7, 3, 6. Okay, so it's really implementation dependent. We can't tell from just looking at it. The standard imposes constraints on operations like pushback. Constraints are called amortized constant time, which means that the underlying buffer of a vector needs to grow exponentially. And since I mentioned that, let us quickly recap how a vector works. So what we see here is a vector object over time from top to bottom. We start with an empty vector that doesn't have a buffer, neither a size nor a capacity. Then we add some elements to it. The vector will automatically reserve a buffer, and these objects that we add live within the buffer. Okay? The buffer can be larger than needed, in which case the capacity, that's the size of the buffer, exceeds the size. Now, when we reach the capacity and we add more elements, the vector will need to reallocate new memory and move or copy the existing elements in the buffer to the new buffer. Now, short question, when is it a copy and when is it a move? Yeah, right. When the move construction is no accept, then we can move, otherwise we need to copy, right? Okay, and the last bits that depicts the clear operation. So if we call clear on a vector, then we throw away all the elements, but we do not throw away the buffer. And this way of interacting with the underlying storage is important for like most of the techniques I will show you. Okay, but that doesn't answer the question how many times this snippet will allocate. To do that, we'll go and look at an example. Is that large enough, or shall I? Sorry? Yeah. Like that? Okay. Okay, so this is exactly the snippet that you've just seen on the slide, right? With the exception that I have some bogus return statement here at the bottom. It doesn't make any sense, but this was my attempt from keeping the optimizer from throwing the vector away. It works. Okay, so let's compile it. And now our first attempt will be to use the debugger to figure out how many times it allocates. So we might say, you know, I don't really know which allocation function it will use, so we can just like use a regular expression and, oh. That's not really helpful. So it will break basically everywhere because we have lots of symbols with alloc in the name. So we don't do that. Now, instead, we go for the real malloc that we know. Might be a good shot to also use aligned alloc because that is invoked from time to time too. Now, if I start the process, that's still not super helpful because if I look at the stack trace, this is not coming from the main function. This is the startup of my whole thing, right? So I don't want to know all of that. Let me disable the breakpoints and set one at main because this is where we start caring about this. Okay, now we are here. Now we enable them again. And we continue execution. So this is malloc. Backtrace leads us to, this is what we want, right? We start at main at the bottom and then alloc, blah, blah, blah. And then operator new and then malloc. Okay? Now, if we quickly recall, malloc is a simple function. It only accepts one parameter. That's the number of bytes. We don't have debug information available here, but the first function argument on this platform will be in RDI. So we can read it out. And it's 4 bytes. That makes sense, right? We just pushed back an integer. That's 4 bytes. That's nice. Okay. Now, next time we are here, it's 8 bytes. Next time, okay, 16 bytes, and so on and so forth. And we will, okay, that was 8 times, but still a bit, so the answer is 8. But it was still a bit manual. So let us see how we can do a bit better. We can just record these steps in like a debugger script-like file, okay? So we were setting breakpoints. Now we forget about aligned alloc because that didn't really come up here. We give it a name, which makes it easier to refer to it. It shouldn't be enabled by default in the beginning. We want some output whenever we hit malloc in order to trace this. So there was register, reach, RDI, and then process continue, done. All right. Now this is LLDB specific stuff, but you can do the same in any debugger, right? You record a command that is executed whenever we hit a particular breakpoint. Okay, cool. So the other breakpoint we needed was main. And we want the main command break to enable the other one. And then we want to launch the application. Now, let's see whether that worked out. So we can start LLDB in batch mode and pass that script along. Okay. So that's basically the same. I don't know how to get rid of the extra verbose output there, which would be nice, but anyway. So this is cool because we can now use pretty basic debugger interactions to record the malloc traces for a particular function. You would also want, and using this breakpoint enable technique, you can really pinpoint a particular function and then also set a breakpoint when this function returns and disable the malloc once again, right? To not, when you have a larger program. It worked for this small one, but that's really helpful. Okay, all right. So we have an answer, let's continue. This is just a recap. So whenever the size of a std vector or std string, but really any container that has a dynamic contiguous sequence is known, we use the public API to reserve this capacity upfront, right? Okay. If, like I've certainly seen usages of reserve that were a bit cryptic because sometimes it's not really clear from the context what the numbers mean. If that's the case, please comment to make it clear that this doesn't come from nowhere, but rather it's justified to use a particular number. Okay, I'm also not the first one discovering this, so you can look it up, item 14 in effective STL. It's basically the same tip to avoid unnecessary allocations. Okay, then we have a gotcha. Does anyone know when we should never call std vector reserve? It has something to do with loops. So we shall never, almost never, call reserve in a loop, because this, if we were to comment this line in, we destroy the exponential growth of the vector's buffer, and we allocate 100 times, or could be a bit less because the vector isn't really constrained to give us exactly this buffer size that we request, but it's bad. Yes?
I saw one code base that intentionally did this to make sure that they never over-allocated, and it made me nervous. I'm just curious what your opinion was there.
Yeah, comment was that it might be use case to do this intentionally to never over-allocate. I mean, it could, I see a use case when performance isn't important, but the heap is very constrained, right? Then, yeah. But I assume it would, depends on the context really, but then I would assume if one would to pre-compute the required size before the loop, then reserve, then enter the loop, it would probably be beneficial, yeah. Yeah. Yeah, right. The comment was on memory fragmentation, and if we repeatedly allocate, then the memory might end up being anywhere. By the way, it's a good we haven't really talked about the specific value for the vector growth strategy, right? And it's an interesting question to ask whether 2 would be a good value. Like every time we need to reallocate, just double the vector size. And it turns out to not be very suitable, because if you use 2, then you will never be able to reuse the buffers that you allocated before, because they will never fit. If you use something between, let's say 1.5, you allocate like a chunk, next chunk, larger chunk. At some point, you will be able to reuse the one, like a combined chunk from the beginning, right, of that, if we think of it as a sequence. Anyway, there's one more thing that's good to know about reserve. Are there other reserve member functions that we should be aware of? Well, yeah, but that's resize. Yes, I mean, it's useful. It does something similar, but no, I'm specifically asking about reserve. Okay, std_dec doesn't have reserve, std_list doesn't have reserve. Doesn't make any sense. But unordered map has, and like the multi-map and unordered set and so on. They do have reserve. And what reserve does with these containers is it pre-allocates bucket space. Now it does not, so in this example, the individual insertions will still allocate because it's a node-based container. It has to allocate for a particular node in there. But there is additional space required to store the singly linked lists in the buckets, and we can avoid that by calling reserve. Okay, cool. Recipe number 1, use stack space when possible. That's quite a simple one. So when we have sequential data and we know the size of our data beforehand, we shouldn't use vector, but rather std array, right? Std array will use stack space, and that's good because it doesn't allocate. Now, sometimes it might be weird to have like the literal size everywhere, might make the code less reusable. So you can carry it around and parameterize your functions or classes on that array size. But I tend to not overdo it because then I have to turn everything into a template, and you know, there's usually a better way to do it. It's more interesting, like thinking about stack space versus heap space. It's more interesting to look at std string, where it becomes less obvious. Oh, wait, I'm not there yet. Right, there's another thing about stack and heap. We might, so if I declare std array as data local to a function, I can be sure that this will always live on the stack, right? In this case, I can't really control it, right? If clients create an object, an instance of this class on the heap, then it will not be stack allocated at all, right? So keep that in mind. You can't control how clients use your data member. That being said, in more effective C++, there's an item on how to constrain clients from constructing your classes on the heap or force them to do that. It's a bit hacky, but I guess I would argue when I end up needing to do that, something else is wrong. But anyway, it's good to know of the limitations of using std array. Okay, but now string. All right. Now we have a pretty bogus string length function here, and the question is, will this function allocate? Of course, the answer is it depends. But let's see what we can do about it. Now, oops. This is the function, right? We will compile it with optimizations enabled because that's what we care about. And now, if we look at what we have just compiled, we don't need to read assembly. I mean, I'm not the person who reads assembly for breakfast. So we can just look, because it's only that one function in the binary, we can look at the symbol table. Oh, we should pipe it through some demangling. Right, that's it. And we see operator new, operator delete, mem copy, string length, of course. So yes, we can say that there's at least one path where this will allocate, which makes sense, right? Because std string is an owning string, and of course, if the string is long, it will allocate. But let's figure out when exactly, okay? Now I've written a small main function that uses this strange string length function that just passes on the first command line argument, okay? Okay, so now I can do this, but I still don't know whether it allocates or not, okay? Enter DTrace. DTrace is a tracing tool that comes from the Solaris world. It has been ported to macOS. There's ongoing work to port it to Linux. For me, it's one of those tools, like same category as Inkscape. Like it's great, but then you don't use it for 2 months and you start by 0 when you touch it the next time. But anyway, you can write DTrace scripts. Doesn't make much sense to go into all the details here. just this. We use the syntax is a bit like awk, but we use a PID provider here, and we give some more specifications where we want to trace what. In this case, the PID provider will only inspect the process that we're interested in, and then on every entry into the malloc function, it will execute this little body there. In this case, we have a look at the first argument of the function, which was the number of bytes being allocated, and we also would like to know how many times it is called, all right? And then, much like awk, there's an end clause, and we can print out some statistics. Okay, now what we will do, so we need some privileges to do that, because it hooks into the kernel, and I think it patches the binary on the fly, which is crazy if you think about it, but it works. So we use this script and execute this command with the privileges of the DTrace command, which in real life you should probably execute like the program that you want to trace and observe with ordinary user privileges. In this case, I just compiled the binary. I know what's in there. We can do it, but yeah, just a word of caution. Okay, now it doesn't output anything because it didn't allocate anything, right? DTrace by default starts measuring starting from the main function. Okay, we can configure to do it differently, but in this case, that's what we want. Now we can just pass some long string and right, we allocate it. Okay. Now this is using libc++. Does anyone know where the boundary is for the allocation? Yeah, I think it's 23 plus 0 byte. Okay, A, B, C, D, E, F. Now this is 17 bytes, doesn't allocate. Still doesn't allocate. There we go. And this is, yeah, this is 23 plus the 0 byte, okay? And you might be knowing what I was like trying to point out here. Std_string has a small string optimization buffer that lives within the object itself. And depending on the standard library implementation that you use, you should be aware of that. I don't think it's necessarily good practice to say, you know, I assume that we will always use small strings, so I never need to worry about string allocations because that's in the SSO buffer. That's probably not good, but it's worth knowing about. And when the scope of the string you're using is small, I guess it might be fine to say, you know, I don't care about it because we have SSO. Okay, if that doesn't cut it, you can reach out to an array of characters, obviously, or use something like boost static string. Cool. Next recipe is use views whenever possible. And I'll point out a couple of advantages that I see when using views in your interfaces. The first one being that they don't allow you to make accidental copies, okay? In this example, I mean, I've seen it happening. Sometimes we do forget like a little syntactical detail and we end up copying something. That just can't happen if you use a view. Second, it gives us choice over it gives us the choice to pick the right container for the circumstances on the call side. Okay, it might be a vector, it might be an array, it might be something else. As long, no, with the function signature on the top, as long as it's contiguous storage, we can pass it to the function. So I suppose it's a good design principle in the first place to constrain your signature to what you really need, right? It doesn't have to be a vector if you just, I don't know, iterate over it, do something with the numbers or whatever, and then don't use it otherwise. View interfaces also don't offer copies. So if we, for example, it's not possible to use a string view to implicitly construct a std string because that would potentially allocate and so on and so forth. Same with substring, which is the example here. So the string view function will never allocate because substring returns a subview as opposed to std_string, which returns a new object that owns. Okay, 2 gotchas with views. One, what happens if we need to copy the input sequence? Now then, this recipe doesn't really apply because we can do better than this. In this case, if the caller was to pass a std vector, we could really avoid the copy by moving it into the function. And that's why, in that case, you could consider offering a second overload, not only the view function signature, but also like a specific container. When we want to use move semantics, then we need to commit to the particular container, in that case, std vector, and then we could move it into the function, and the compiler will figure it out for us, which function signature to choose. Okay. Second gotcha with views, like obviously take care with lifetimes, but it's not so much of an issue with what I've shown you because those were like input parameters for functions, right? Okay. Recipe number 3, use the right constructor. What does that mean? Here are some constructors. Just use the right one. Quickly upfront, of course, that implies using a move constructor if you can, but this is not what this is about, right? Because that's rather obvious. Rather, let's look at this. Are there any options how we could improve this in terms of allocations? And I don't mean call reserve, because we already had that, and now I'm thinking about something else. Okay, so what we can do is use a vector constructor that works with 2 input iterators. And that allows us to allocate once in the beginning and then do our operation, okay? And we can have a look at the lib C++ implementation for that. This is the std vector constructor that is called here. I removed all this finne to dispatch on input iterator versus forward iterator. And we can see that it calls std distance to compute the size and uses the size to allocate upfront. So what I had in mind will really work with this. And another interesting detail of this implementation is something that I didn't expect. I was expecting a further dispatch on random access iterator versus forward iterator, right? Because if you call this constructor with iterators into a list, then it will happily walk the whole list to compute its size. Well, std list size is constant time, but if we only have the iterators, it's not, right? So we will have to iterate through it and then go through it again to construct all the elements, which is a bit surprising, but I guess there are trade-offs and you can come up with examples where both scenarios are, I know, better or worse. Yeah, okay. We can go one more step and combine the past 2 iterators with the operation we had in mind. One way to do it is use boost transform iterator. Unfortunately, I believe the transform iterator implementation pulls in boost one of the C++98, I think boost fusion, like one of the compile time heavy old meta-programming libraries. So the more modern way of doing it, if you can use it, is a view. So we construct the view, a transform view, and then pass iterators into that. That will achieve the same. Okay, nice. All right. Now we have seen the small string optimization for std string. And now the question could be, can we have the same for std vector? And yes, we can. We can use what is usually called a small vector, which will have a configurable stack buffer. And whatever fits in that stack buffer will live there until we exceed its capacity, and then we'll go to the heap. All right? So in this example, The first 3 pushbacks won't allocate, but the last one will, because we just exceeded the stack capacity. Okay, I have a benchmark for this to see it in action. There we go. It's not long. It's using Google Benchmark. We have a populate function that will just repeatedly push back. Okay, that's all it does. And we do that for several sizes. And we instantiate the function for std vector of an integer type, and then small vector, also integer type, and 10 elements on the stack initially. Okay, now let's compile that. Oh, I need to link against benchmark. There we go. So the first numbers are for std vector. Second is for small vector. So we can see that for small sizes, the small vector massively outperforms std vector, because, I mean, this code doesn't do much apart from allocations. So if we can use the stack capacity, then we don't allocate, and that's good. And you could argue that I told you 10 minutes ago that we should always resize, and that's probably the right thing to do. So we resize now and see what happens. And there we go. Small vector is slower, which is maybe a little bit surprising. I thought that at least for the small, yeah. Oh, sorry, yeah. Thanks. Yeah, right. So here for the small size, the small vector is still beneficial, but as we grow, you not only see no difference anymore, std vector is actually faster. And why is that? Now recall what we do. We call pushback all the time. And if we have, like in a std vector, there's only ever one buffer that is usable. In a small vector, there need to be a runtime dispatch querying, like, are we using the stack buffer, or do I have to go to the heap buffer? So there's some branching going on, and that's, I guess, not so beneficial. Which leads me to the conclusion here. Small vectors are great for saving allocations, but they need, like the name implies it, they really need to be small. They do come with a cost, which is the additional branching. And since we recap all what's important about small vector, keep in mind that small vector might be a syntactical drop-in replacement for std vector, but it's not in terms of the semantics. So it will always need to have different, will have different behavior when it comes to iterator stability and stuff like that. Okay. Next one. What can be done better here? We have a loop, and within the loop, we get some data. This might be an easy one. We can pull the vector out of the loop, clear its content at the beginning of the loop, and then change the function signature for this example to operate on some mutable state. Okay. This works. It's really effective. We reuse the capacity all the time, but we are also entering like some kind of danger zone here. Everything I've shown you so far, I would argue that we can relatively safely apply it without the need to properly justify what we are doing. That is over now. Everything we do now is somewhat more intrusive. And in this case, we are violating some good practices when it comes to variable scope. Okay, there's a nice chapter on this in this book. And whenever we want to apply such a technique, we should really ideally have a benchmark that shows how beneficial it is. Okay. Very similar one for this situation. Can the buffer behind this vector be reused. Now, it's not a free function anymore, but a member function. Yeah, the comment is the member function is const qualified, so we run into trouble. Yeah, drop the const. Yeah, so we can promote this local variable to a data member, and then we clear it in the beginning of the member function. We certainly lose the constness, and there's something to discuss about it. If you recall, I think it's item 3 in effective C++, use const whenever possible. Scott Myers distinguishes between logical and bitwise constness, and says, the compiler enforces bitwise constness, but we should make intuitive interfaces. And when we have functions, member function signature, that doesn't change any state that would be observable, intuitively observable from a client, then it should be const. And if we use a cache within that member function to implement it, that's an implementation detail, and we can mark it mutable. But the book is also somewhat from the time where multi-threading wasn't everywhere, right? And we would probably want to argue that when I have a mutable data member and I mark a function as const, this member function could be perceived as thread safe, and it will be used from multiple threads, but it's not, right? So whenever we do that, and I have Herbsetter here because he commented on that in his "You Don't Know Const and Mutable" talk, and I think it's the way to go. And that's why we need to add this word of warning here. Whenever we do that, we need to justify losing the constness of a member function. Of course, it's not already, if it's not const in the first place, then no problem. But if we lose it, then this is something serious, and we need to either protect against race conditions, but I would guess if we throw mutexes at it, then the whole optimization is kind of like we missed the point, right? And we could, in addition, comment on what we are doing and give some hints to whoever reads the code after we've touched it. Okay. How do we promote scope of data if we are in a free function? Okay, I already give it away. Yes, there's a question. Okay, there was a comment that evaporated, but we'll talk about thread local storage right now, because I already give away the answer to these questions. So we can use thread local to have something that persists within, in this case, like some compute intermediate data used as a scratch buffer. And whenever this function is called, possibly from multiple threads, it can reuse this, right? A better alternative, there are two alternatives though. We could also pass in the to be reused buffer from the call side, but I would argue that then we are leaking implementation details, which we wouldn't want to do. Maybe a better way is to pass in polymorphic memory resource, but we haven't seen it, so I just want to make sure that we don't forget about thread local, because it can be a valid option. Again, if we prove that it actually does what we want it to do.
One of the big downsides of thread local is that when it was introduced, everybody used threads as a mechanism to separate out chunks of work. Since we got coroutines in C++20, we can suspend work on one thread and resume a different task on the same thread, which means that both of those tasks will be using the same thread local buffer and still conflate.
Okay. Yeah, that was a comment that pulled in coroutines, and I don't want to comment on that because I don't know what I'm doing when I'm commenting on that, but let's discuss it afterwards. Okay, next one. We have a couple of wrappers around around containers. And we should keep in mind that the backend implementation of these is customizable, all right? Std stack is a good example. There's also std priority queue, stuff like that. You can inject your own container. This is an example for a use case where the stack will never allocate, right? We also need to make sure that we never put more than 10 elements in it, but this is doable. There are more library-specific options. For example, if you work with linear algebra types like matrices, which are often not resizable in the case of OpenCV or eigen, you can use resizable data structures on your end, like a vector, and then do some magic in order to fit it into whatever this library needs, okay? This is very specific to these two libraries, but it can be very useful if you need resizing stuff and reusing capacity, all right? Here's an example for a lookup table that will never allocate. Again, we use static vector for that. Std array doesn't work because we still need the notion of an allocator. And we configure a flat map from Boost with it. And that's quite useful if you have like some local lookup going on and you don't really see the need to allocate because you know how big it will be, the kind of storage you need. So that's good. Okay, that leads to the next recipe, flat map and flat set. They are syntactic drop-in replacements for their standard counterparts, but really they work like a vector. Okay, and what's nice about those is that all the tricks that we have seen so far can be applied to them. We can use scope promotion, like to pull it out of a loop. We can use reserve to pre-allocate space. We can make it a data member. This kind of stuff, it works with flat map and flat set, okay? Right. Okay, I think I need to speed up a little bit here. Okay, now, monotonic PMRs for node-based containers. We'll start with an example again, and I will switch to Linux VM here. So PMR, what do we have? Stack R. Okay. So some main function. We start off with an ordinary map that doesn't do anything special about its memory, all right? And we reserve the bucket space, you know, because I told you so. And then we just randomly insert stuff, okay? Then we make sure that it doesn't get optimized away. And let's quickly compile that. Wait. Okay, and see what it does really. Okay, we don't need any kind of call stack hierarchy here because everything will be inline anyhow. So what we see here, now this, I profiled the app and we see where it spends its time basically. So we see malloc at 4%, and then this guy here, which is, you can't really see it, and I don't know whether there's a way in this UI to like scroll to the right, but this is the destructor of the node, the tree implementation of std unordered map, okay? And that's quite common for code that uses hash containers, standard hash containers, because they are node-based. That means whenever we allocate, we need to like allocate individual nodes, but also when we deallocate, we need to loop over all the nodes and, you know, give that memory back. So that means we can do better. And let me go back to the slides. We want to use contiguous storage or semi-contiguous storage for that matter with these hash map and set operations that offer some advantages over flat map and flat set. How do we do that? Now, this is an example how to construct an unordered map with the monotonic buffer resource. That's a resource that will allocate buffers in chunks. You can pass it your own buffer. You can let it allocate its own. When it runs out of a buffer, it will allocate the next, use some growth strategy again. And that's really useful for our example here. But first, we need to know how much memory we actually need, right? Because std unordered map is like, it needs more than just key value pair. And in order to get some idea about it, I measured this using another PMR resource that would just, print what it allocates. And what we see here is on the x-axis, it's just an increasing number of items in the container. On the y-axis, we have the additional bytes in addition to std pair key value, okay? All the bookkeeping, but it doesn't increase because I normalized it over the number of items, if that makes sense. Okay, so what we see is that it allocates some space for the bookkeeping. If it runs out of the space, it will allocate more and so on. And the bigger it gets, the less frequent these bookkeeping allocations occur. Now, what we really need to pull out of this is some kind of estimation on when we have a std unordered map and we want 200 elements, how much bytes do we need, knowing how large key and value is. Interestingly enough, it doesn't scale with the value size, the size of the value type, but only with the size of the key type. Now, to wrap things up, this is how I would like to use it. We will come back to the size, like how much we need to allocate later on. This is an API that I would have in mind if I want to use a std unordered map with a PMR memory resource, in this case, key and value, both integers. And I want 200 elements on the stack. And if we exceed the stack space, then we will allocate like a bit more than 200 on the heap, all right? And this is how it can be implemented. So we see the buffer size that is computed as number of elements times the size of the pair of key and value, and then 5 times the size of the key. That's the intelligence I extracted from this plot from the slide before, right? And then it sets up a std array and creates a monotonic resource from that buffer. So the initial buffer is on the stack, and then it also creates the map for us, passes a pointer to the memory resource, and returns that, okay? And this is what we will use in our example here. Wait. Okay, so I have the implementation somewhere here. Right, this one. Okay, I just copy how it's used into here and replace my usage of std unordered map with this one, okay? So that's good. Let's save this one for now. Let's call it no PMR.out. Oops. And PMR.out. Okay, so we can I mean, it will work exactly like the other one. It doesn't print anything, but we can get the timing, and then the timing of the other one. It's like the number of elements that we are processing here is large enough that I think we don't need a benchmark that runs repeatedly. It's just to get an idea, right? So we can see that the PMR technique for std unordered map really outperforms the std unordered map without any kind of customization. We could also look at how much time these two executables spent in the memory allocation system calls. So since we are in Linux here, we can use strace, and we will look at the timing, sorted timing of all memory system calls, okay? And we want to do PMR.out. Wait, we start with the other one. no PMR, and then we do with PMR. Okay, and what's interesting is the number of calls that goes down quite substantially for a map here, right? And the time we spend in these calls also goes down. So that's quite nice. To be fair, as always, this applies. We don't do any work on the data. We just insert stuff. So it's always usually not representative of the scenarios that we encounter in real life, but still it's good, you know, to get some evidence of our techniques that they work, actually. Okay. Okay, this works well when we don't erase elements, right? If we do so, then we waste a lot of space because we have a monotonic buffer resource that will only ever grow and never really give individual nodes back to a memory pool or anything. Okay, last example. I'm running a bit out of time. And I think I should maybe just skip it because if I go through it super quickly, then it doesn't make much sense. Or do you want me to? Yeah, okay, I see some thumbs up, all right. Okay, I'll try. This example is about using std unordered map again, but with different requirements. Here we have a nested container, std unordered map, with some vector in it. And we will use PMR namespace containers again. That means std PMR unordered map of something mapped to std PMR vector. The allocators we construct there, they propagate. That means we use the same allocator for both containers, which is a nice property. And we'll have a varying memory footprint of the application. So what I have in mind here is clustering of points from a laser source, okay? That's like something you would do in robotics when you have a robot that has a laser and it gives you a point cloud, and you filter these points by whatever algorithm, and then you need to turn it into like groups of points, okay? You would project these points into the ground plane. That's what you see on the left, you know, where you have a binary measure. This cell is occupied or not. So I will put a grid onto my ground plane. Say this cell is occupied, this one is not. And then invoke some connected components algorithm to turn these into distinct groups. Okay, and then I need to map it back to my points in order to create like a bunch of points that belong together, because beforehand I didn't have that information, all right? Now what I need is a mapping from a 2D grid cell index to one or more points. It can be quite sparse, so std unordered map is a good first shot, really. And this will be our clustering strategy class. I try to keep it as simple as possible, so we would do, like, call it compute clusters, X and Y coordinates. In this case, as we project everything into the ground plane, we don't care about like the height, right? And we need some cell size, number of cells per site. Okay, this is how it is implemented in the first version with std unordered map without any memory resource passed to it. And we'll end up, you know, taking each point, compute the index, row and column index of our grid, and then store that in the hash container in order to be able to look it up later on, okay? And now the thing is, in this scenario, I can, like, the size of my input data can really vary. Can be 100,000 points and can later be 10,000 points. And the data is so large that I don't want to waste memory by always going, you know, if I applied these techniques that we have seen so far, I would go, okay, just reserve max capacity, and then we are fine because we don't allocate, right? We don't want to do that, but rather be able to adjust to it. So what we can do is use a custom memory resource that keeps track of how much data it allocates. And in order to do that, it will just keep track of how much memory it allocates. Then we can implement some kind of growth strategy or just some safety factor. And then every time this clustering algorithm is called again, we will allocate as much as we believe is needed. And that works quite nicely. This is the custom buffer resource. So it's really simple. We just count the number of bytes. In production, we should really also like take care of overflow and stuff. But for this example, it just works like that. And we can save the memory footprint over time and then insert that in our algorithm, and we get much better performance out of it, which is nice. These are where my images come from, and yeah, do ask questions. You have no minute left, I'm sorry.